PowerPoint is restarting. Okay, thank you. So, this is a scatterplot. Scatterplots are simple and probably the most common way to represent the relationship between two variables in a data set. Of course, there's other ways to represent a two-dimensional set of data, such as histograms or contour plots. But scatterplots have a couple of nice properties, such as a one-to-one mapping between the data and the representation. You can count the points to get a sense of scale or changes in scale. And they allow for easy selection and filtering of the data. However, scatterplots do suffer from a pretty serious problem. When looking at too many data points, the data points obscure one another, making it impossible to discern the underlying data distribution. And this is referred to as overplotting. So there are ways to mitigate the effects of overplotting, such as removing the fill of the marks, or changing the shape of the marks, or making the marks smaller. And these techniques work in some situations, but in cases where you have either very many data points or a very small chart, you still end up with overplotting. So to deal with this, the chart designer needs to go find the setting for the individual mark opacity and manually adjust that slider until the chart looks good or properly represents the data. This isn't ideal when working with a single chart, but it can be done. But in situations, like dynamic situations where the number of points may change or the distribution may change, it's definitely not possible to always be going in and manually setting new opacity values. So what we wanted to do was find a way to automate this process of finding suitable opacity values. So our first step was to see what people do when they're trying to make the chart the most appropriate. So we ran this study where we asked participants to adjust the opacity slider until the chart looked the best or presented the best representation of the data. We controlled for two factors in our procedurally generated scatterplots. The first was the number of points between 1 and around 20,000. And the second was the distribution of the data within the chart. We ran this study using Mechanical Turk, where we started off with 46 workers, and we were left with 31 after we kicked those out who were trying to game our system. And if we look at the results, starting with the wide distribution of points, I mean, in general, it's what you would expect. When there's less points and less overplotting, users prefer a higher individual point opacity value. And as there's more points and more overplotting, you use a lower opacity value. And we get a similar curve for the medium distribution, only slightly lower, and again, similar for the narrow distribution, but lower still. But if we look at a single number of points condition, we can see what the actual resulting charts look like. So in this case, with 1,700 points, we can see users were using a 27% opacity level on the wide condition down to a 10% opacity on the narrow condition. So clearly, the distribution of points has an effect on what opacity level is most suitable. So our next step was to look at all these resulting scatter plots and see if we could find some visual characteristic of them that we could use to model the user's behavior. And we want that characteristic to be consistent across the different distributions of data and the different number of point conditions. So we looked at a couple of properties which didn't have that characteristic. You can see the lines diverging for the different distribution types. But then we looked at something which we called the mean opacity of utilized pixels, or MOUP. So basically, rather than looking at all pixels or the entire area of the chart, we only look at those pixels which actually had data plotted on them, so those orange points there, and then we calculate the average resulting opacity of those pixels on the chart. And when we look at that metric, the MOUP metric, we get this fairly remarkably flat line around 40% over a wide range of the number of point conditions, and doesn't show any particular bias for any of the distribution types. So to make use of this property, we need to come up with some way to generate scatter plots such that the resulting MOUP is around 40%. And so there's some math in the paper, but in words, I mean, what we're doing is searching through the individual point opacity values to find the one which generates a chart with a mean opacity of utilized pixels closest to 40%. And when we do that, the results turn out to be quite closely match the user results. So these are the user determined preferences, and when we overlay the results from our model, the correlation is quite high, and we have similar results for the medium and wide distribution types. So of course it's fine that we collected data from one set of charts, generated an algorithm to reproduce those results on that same set of charts, but to be useful, it needs to be applicable for other arbitrary charts as well. So for our second study, we used these 4 data distributions, and we also looked at some different chart and dot sizes. So we used the same small chart and small dot that we used in our formative study, and also two larger sizes. And in the first study, where we ended around 20,000 points, in the second study, we went up to 48,000. So I encourage you to look at the paper and zoom in on this figure if you want to see all the nitty-gritty results. But in general, we had our model matched the user results from this study quite well in all of the conditions we tested. And just as a concrete example of what the results actually look like, this is a set of scatter plots over a varying number of points using sort of a default 100% opacity level. These were the charts generated by our participants, and these are the charts generated through using our technique. So as for what can be done next, we looked at scatter plots using black points on a white background, and that simplified our opacity calculations. But we need to extend this to colored points and colored backgrounds and see if the algorithm needs to be tweaked at all. And also, scatter plots aren't the only kind of chart that suffer from overplotting. Here's parallel coordinate plots. So we need to see how this technique would be modified to work with other chart types. So thanks, and I'm happy to take any questions.
Hi, Tim Dwyer, Monash University. So you chose a single opacity level for every dot in the display. I can imagine one problem with that is that opacity levels that look good on clusters, show the detail in clusters, could make the outliers completely disappear. Did you think about differential mappings of opacity to different types of points?
Yeah, it's interesting. So some of these other types, like heat maps or contour plots, might do a better job of or you could combine different types of plots to show both the details in the deep clusters and the outliers. We were just trying to do a simple, one-to-one mapping. But yeah, that might be a good idea to, somehow optimize for the dense part, but do something to highlight the outliers.
Blaine Harrison, WPI. This is kind of optimizing for user preference, but what about tasks that people use a scatter plot for, like correlation, cluster detection, mean, and that sort of thing? Yeah, no, that would be a great test to run, or study to run as well. So initially, we're just trying to make them look good or perform well. It's also that we don't think there's a objective best value, because like the previous question, you could optimize to see all the detail in the clusters, or you could optimize to see the outliers. So it's not clear what the best value would be. But so yeah, it might be nice to take these charts and see how they compare to ones that were, say darker or lighter for specific tasks. Yeah, hopefully preference and task align.
Yeah.
Okay, thank you, Justin.